To the ancients, who lived largely outdoors, the stars were a mystery. They had no idea of their nature, their origin, or even their distance from the Earth. Starlight carries more clues than you would at first expect. By studying it and combining it with our knowledge of matter, we can gain an insight into stars. The first clue we notice is that stars vary in brightness. Is this due to a variation in distance, or the amount of light the star gives out, or both? Isaac Newton started by assuming the stars gave off the same amount of light as the sun. When their brightness was compared to Saturn, he realized the stars were huge distances away. No one had realized the universe was so vast. In the 19th century, telescopes confirmed what early astronomers had suspected. The closest stars appear to move back and forth against the more distant ones as the Earth orbits the Sun. This apparent movement, known as parallax shift, can be used to calculate the star's distance from the Earth. The further a star is away, the smaller its parallax angle. For stars more than 300 light-years away, the angle is so small that not even modern telescopes can measure it accurately. So parallax angle is only useful for measuring the distance of the closer stars. By measuring the distance of stars from Earth, we can show that they give off different amounts of light. The stars of the constellation Cassiopeia illustrate this. They all appear to have the same brightness. However, they are different distances from the Earth. So the furthest ones must give off more light, or be more luminous, than the closest. Luminosity is the actual amount of light that a star gives off. What we see on Earth is a star's apparent brightness. In the Southern Cross, the closest star is not the brightest, so more distant stars have greater luminosity. Astronomers have always been intrigued by stars whose brightness varied over time. They found that some are binary systems, where a dim star eclipses a bright one. Some stars are orbiting a black hole, with gases being pulled off in great streamers. They are distorted, and therefore brighter from one angle than another. Stars like the Sun vary their luminosity. Every 11 years, sunspots increase their activity, and the Sun becomes slightly brighter. Cepheid variables vary much more than the Sun. The Cepheid's period, which is the time it takes to complete a cycle, is directly related to its brightness. The ones that are the brightest vary the slowest. Using various methods, astronomers worked out the approximate distance of certain Cepheids from Earth. This made it possible to calculate the distance of any other Cepheid by looking at its period and its brightness from Earth. So, if we want to know how far away a cluster is, we look to see if it contains a Cepheid. The next clue we get from Starlight is colour. With time exposure, astronomers saw that the colours of stars are subtly different. The question was why? When they looked at the stars through a prism, they could see their spectra. In the spectra, they saw something they recognised. The spectra were produced by bodies of different temperature. So, a star's colour tells us its temperature. This is the spectrum of a red star. It's the same as the spectrum emitted from a gas that is red hot. The spectrum of a blue star has most of the energy in the blue to ultraviolet region. The star is blue hot. The hotter stars are much brighter. The sun is yellow hot at 6,000 degrees Kelvin. When we look more closely at the spectrum of a star, we see black lines where some colours are missing. These are Fraunhofer lines, named after their discoverer. This is an absorption spectrum. If we heat up an element, it gives off distinct wavelengths of light that make up what are known as emission spectra. They are the unique fingerprint of an element. The black lines in the absorption spectra from the stars exactly match the emission spectra of their elements. So the Fraunhofer lines tell us which elements are in the gases surrounding the star. When astronomers first examined the spectra from the Sun, they found that it is made of hydrogen and helium. It seemed reasonable to assume then that the energy of a star somehow came from these elements. They quickly worked out that the energy comes from nuclear fusion reactions. Gravity increases the pressure and temperature inside the core of a star until hydrogen protons fuse together. Then one of them decays to a neutron. Another proton fuses, forming helium-3. Then two helium-3s fuse to become helium-4. In this process, some of the mass is lost and converted into a vast amount of energy by radiation. This radiation and the expansion of the hot plasma balance the contraction caused by gravity. The fusion reaction happens only in the core where it is hot enough and the pressure is immense. High-energy gamma rays are given off, but they cannot go straight out to the surface because they bounce around randomly inside the star. It may take 10,000 to 1 million years for the light to eventually reach the surface. In this time, the wavelength changes to mainly visible light. In small stars, where there is relatively little gravitational pressure, fusion produces only red heat. A mid-sized star, such as the Sun, is yellow hot. A blue star is more than 10 times the mass of the Sun. Under huge gravitational pressure, the fusion rate is extremely high. The star becomes blue hot, and each square metre is far, far brighter than the same area on the Sun. On top of this, it has a much larger surface area. Each blue star in the Pleiades, for example, has 20,000 times the luminosity of the Sun. In the 1920s, astronomers plotted the colour or temperature of stars against their luminosity in what is known as an HR diagram. Our Sun has a solar luminosity of 1 and a temperature of 6,000 degrees Kelvin. Stars cooler than the Sun are dimmer, while hotter stars are brighter. These are referred to as main sequence stars. But standing out from this logical order were some dim but hot stars. They can only be dim because they are small. In these so-called white dwarfs, normal fusion has ceased. Also puzzling are bright red stars. How could this be? If they are bright, they must have a large surface area to give off that much light, so they have to be big. But big stars should be blue, not red. So these red giants can't have the normal hydrogen fusion reaction either. We begin to solve these puzzles by plotting the stars of several different clusters. Clusters are born in nebulae. They are giant gas clouds of hydrogen and dust and are only just beginning to form stars. If we plot these stars on an HR diagram, we see that they are relatively cool. Only some of the stars have begun their fusion reactions. The gas in a nebula continues to collect and form stars to become an open cluster. We know that open clusters are relatively young because there are still hydrogen clouds between the stars. All of the stars in this cluster are on the main sequence. A globular cluster is old. There is no hydrogen between the stars. We see no blue or white stars, but there are red and yellow stars, as well as red giants and white dwarfs. This suggests that the blue and white stars have used up their fuel and disappeared long ago. Further observations reveal that stars move through various life stages. Yellow stars become red giants and then white dwarfs. Small red stars have relatively low pressure in their cores. They should take about 1,000 billion years to use their fuel. Then they should cool and shrink, becoming black dwarfs. There are probably no black dwarfs in the universe, as the universe is just not old enough. The Sun is 5 billion years old. Yellow stars stay unchanged on the main sequence for about 10 billion years. Then they swell about 100 times. Due to this expansion, the surface cools to become red hot. At this stage, they are known as red giants. They still give off a lot of light because they're so large. Then, as this star shows, the red giant blows away its outer mantle of red-hot gas, leaving a white dwarf in the centre. White dwarfs are white-hot, but their surface is smaller than the Earth. They can't give out much light, so they appear dim. Let's look in detail at the life of a blue star. After only 1 million years or so, the hydrogen in the core is used up. The reaction stops and the star collapses, heating up both the core and the gas envelope. Under compression, hydrogen gas in the envelope starts fusing. It heats and expands to form a supergiant. The really big ones become white giants. The somewhat smaller ones end up red. In the core, compression produces enough heat for helium to fuse to carbon and oxygen. Taking 1 million years to complete, this is the first of a sequence of increasingly rapid fusion reactions that produce a series of elements. Each time a fusion reaction in the core runs out of fuel, the star collapses under the force of gravity. With each collapse, the core gets hotter, until the next reaction is triggered and the star undergoes massive expansion. When the temperature reaches a blistering 3 billion degrees, it takes only a few days for iron to form from silicon and sulfur. Iron itself cannot fuse spontaneously to become anything else. As the star goes from one reaction to another, it heats up and cools down, so its position on the HR diagram moves back and forth across the top. Eventually, no more heat comes from the core. The star collapses, falling at incredible speeds, up to 1/3 the speed of light. The core temperature soars, reaching an unimaginable 100 billion degrees. The remaining hydrogen and other fuels fuse together in one last massive meltdown. A supernova, A colossal explosion and the biggest light show we will ever see. It's over in an instant, but it's bright enough to outshine an entire galaxy. Coming out of this chaos are the newly made heavy atoms, such as iodine, lead, gold and uranium. Only a supernova explosion can generate enough energy to make those elements that are heavier than iron. In time, matter ejected from supernova explosions will mix with gas clouds and condense back into the stuff of which everything in our galaxy is made: the stars, planets, and even people. As the Earth contains many elements heavier than iron, we must all be children of a supernova. For all their spectacle, most supernovae leave a faint and very modest memorial, a neutron star only a few kilometres across. And the bigger they are, the further they fall. Some of the supernovae compress even further to become the ultimate cosmic has-been, a black hole. The gravity from a black hole is so great that not even light can escape, so it appears black. We can only detect them because of the massive X-rays given off by matter as it falls in. No one knows what is beyond a black hole, which makes it such a hot topic for science fiction writers. What's on the other side? Another Big Bang? Another universe with different laws of physics? Ever since the beginning of time, we have looked to the stars and wondered about their origins, little knowing that we have much in common. Through analysing Starlight, we can work out what goes on inside them and what their future may be. And we now know we're all made of the same stuff: stardust.